Good morning to everyone. I am Alessandro Nastro from the University of Brescia, Italy. And today I'm going to talk about the research project carried out within our group entitled Electrostatic-Capacitive MEMS Stiffness Sensor with Position Feedback Mechanism. Mechanical properties of biological samples, such as forces or stiffnesses, play a crucial role in many vital processes, such as the mitosis process or the heartbeat process. The knowledge of these properties allows to understand the state of health of cells or tissues. Therefore, tools able to measure mechanical properties are highly demanded. Typically, a stiffness sensor is a device that provides information regarding the stiffness of sample, imposing a displacement while measuring the force required to impose the displacement. Knowing the displacement and measuring the force, it is possible to estimate the stiffness of the sample, placed in contact with the probe tip of the device. This principle has been implemented inside a MEMS device fabricated with the thermal process developed by ST Microelectronics. The reported device has a fixed part named stator S and a movable part named shuttle R, which is sustained by four folded springs. The interconnection between the shuttle and the stator creates a capacitive position sensor. Furthermore, the shuttle can be electrostatically actuated by four variable area electrostatic actuator named drivers. The MEMS device developed has been inserted inside a servo-assisted position feedback mechanism, which block diagram is reported into the image. A sinusoidal sensing signal with the frequency far away from the mechanical resonant frequency of the structure is applied to the stator of the device, with also an amplitude low enough to prevent the pull-in effect. This signal will induce a current at the same frequency of the sensing signal, which is converted into a voltage thanks to a transimpedance amplifier and provided to a loop-in amplifier, where the synchronous demodulation technique is implemented. Therefore, a DC output voltage named VPOS function of the position of the shuttle respect to the stator of the device is produced. This voltage is then compared to an external fixed voltage named VPOS0 thanks to an integration amplifier. The output voltage produced is then amplified enough thanks to an amplification stage and provided to an electrostatic actuator named D2, thus inducing an electrostatic force which will maintain fixed the position of the probe tip of the device. So changing the voltage VPOS0, we can impose the displacement of the probe tip. And thanks to equation number 1, we can estimate and obtain the position of the probe tip. Then, thanks to the feedback mechanism and measuring the output voltage, it is possible to measure the force required to impose the displacement, as reported into equation number 2. Combining these two equations is therefore possible to estimate the stiffness of the sample placed in contact with the probe tip of the device. The working principle of the proposed sensor has been experimentally verified, estimating the stiffness of the springs of the MEMS device without placing a sample in contact with the probe tip. In figure is reported the measured position voltage and the voltage difference as a function of the imposed position voltage. The obtained results show the effectiveness of the feedback mechanism to control and impose the displacement. The electrostatic force required to impose the displacement has been measured as a function and has been reported with the nonlinearity error relative to the span as a function of the position of the probe tip. From the linear fitting of the experimental data, the stiffness of the springs of the MEMS device has been estimated. The obtained value is in good agreement, with the value obtained in previous works. In conclusion, an electrostatic capacitive MEMS stiffness sensor with position feedback mechanism has been presented. The proposed sensor allows to impose a displacement acting on external position-dependent voltage and to measure electrically the force required to impose the displacement. The proposed sensor has been experimentally verified, allowing to estimate the stiffness of the springs of the MEMS device. So thank you very much for your attention and do not hesitate to contact me for further information. Thank you very much.